Hello everyone, my name is Zhang Peng, and my research is focused on the intermaterial compounds decorated on the cellular architectures as a highly active catalyst for the water splitting reaction and the carbon dioxide reduction reaction. Well, as we all know, the energy and the environmental pollution are the urgent problems that need to be solved in this century, and the key to solve those problems lies in the use of the energy and the reduction of the greenhouse gases. As can be seen in these two figures, nowadays the commonly used energy is still the fossil energy, which is also the root cause of the above problems. Well, the hydrogen gas is considered to be the most ideal alternative energy of the fossil energy because the high energy density and the pollution-free during the hydrogen-oxygen combustion. However, the relatively low amount of the hydrogen gas in the atmosphere does not have enough capacity to support the growing demand of the large-scale industrial use. So we need to find some more other methods to produce hydrogen gas. As we can see in this picture, there are four main methods to produce hydrogen gas. It includes the hydrogen production from the fossil energy, the hydrogen production from the biomass energy, the photocatalytic water splitting, and the electrocatalytic water splitting. The first one and the second one is not suitable for us to produce the hydrogen for the larger industrial scale use. And especially in the electrocatalytic water splitting, it can combine with the renewable energy such as wind power and solar cell and others. It can store the renewable energy in the form of the hydrogen energy. And the electrocatalytic carbon dioxide reduction reaction is also considered an effective way to reduce the greenhouse gas. It can convert the excess carbon dioxide in the atmosphere into the energy that people can use. Well, my research objectives focus on the cobalt series compounds decorated on the graphite cellular architectures and investigate the relationship between the hydrogen evolution reaction performance and the electronic structure. The second one is to propel three different kinds of the copper-indium intermetallic compounds and decorated on the graphite cellular architectures to investigate the product selectivity of the carbon dioxide reduction reaction. Well, as we all know, although the electrode technology has been developed for more than 200 years, there are still many challenges awaiting us to overcome. One of the key challenges is the electrocatalyst performance. Take hydrogen evolution reaction for example. The platinum metal is the best materials for the hydrogen evolution reaction. However, the price and the low reserve hydro of the platinum metal in the earth is very difficult to solve for the large-scale industrial hydrogen production. So, design a no-noble electrocatalyst with a high performance is very urgent. The intermetallic compounds is considered to be the promising materials in electrocatalytic field. It can solve the problems that are mentioned above. Well, in the figure 1, figure A shows that a lot of literatures have published. It demonstrates that the several intermetallic compounds serve as electrocatalytic materials. Well, during our experiment, we found that the compounds with a cobalt-rich tangular structure have good hydrogen evolution reaction performance. So we synthesized 4 different compounds with a cobalt-rich tangular structure. The figure B is their crystal structure. They involves the titanium cobalt-2, the zirconium cobalt-2, the hafnium cobalt-2, and the scandium cobalt-2. Well, as shown in the figure 2, nowadays more and more people have been committed to reducing the volume of the bulk materials in order to involve the catalytic performance of the materials, such as nanomaterials or the atomic cluster. However, there are many limitations in the process of the large-scale industrial hydrogen production to use those materials. How to improve the catalytic activity of the materials by the directional construction of the cobalt in the structure have never been studied before, so we have made a bold attempt about it. As we can see in the figure 3, it is a theoretical calculation of the platinum metal, our materials, and the cobalt metal. It is clearly that the free energy of the hydrogen on the cobalt tangular rich materials is very close to that of the platinum metal. It means that it may have extraordinary performance in the hydrogen evolution reactions. Well, the next page is an electrochemical test. We can see in the figure that our materials have the extremely excellent hydrogen evolution performance under alkaline conditions, even better than that of the platinum metal. It strongly confirms our conjecture have made before. Well, the figure 5 is a SEM image of the synthesized materials. It means that our materials are all bulk materials. Well, in order to improve the performance of our materials, we need to coat those materials on the cellular architecture structures. First, the materials is melted to the fine powder, and then the materials is made into the cellular architecture structure by using the microfluidic systems. Well, at present, this work is in the progress. And the figure 5 is coating samples on the cellular architecture structures. Well, my second major research direction is research of the carbon dioxide reduction catalytic materials. As we all know, in this field, the selectivity of the materials to the products of the carbon dioxide reduction reaction is particularly important. So I designed and synthesized 3 different kinds of the cobalt-indium intermetallic compounds. As we all know, the cobalt is the active site of the carbon dioxide reduction reaction. The cobalt atoms is bound to have the different electronic structures in the different structures. It will also affect the activity of the carbon dioxide reduction reaction. And so we synthesized the 3 different kinds of the materials to figure out those combination of the electron structures and the performance of the carbon dioxide reduction. The figure 6 is the crystal structure of those cope-indium intermetallic compounds. Here is a reference of my presentation. Thank you very much for your listening.